So, you want to return a sample of extraterrestrial life to the Earth. You might be astonished at the complex requirements. Your first thought might be, why not just return to a glove box in a biohazard level 4 facility? We know how to handle hazardous biological materials, and that's what the experts thought back in 1978. Well, actually, they would return it to a quarantine facility in low Earth orbit called Antaeus, but a similar idea, just glove boxes. However, soon these ideas began to seem far too simple. First was the discovery of ultramicrobacteria. Here are some more recent results. The ones shown on the left are taken from narrow liquid veins at depths of over 3 kilometers in a Greenland glacier and of interest for astrobiology of Europa. Strikingly, they can pass through a 0.2 micron filter as used to purify water. 0.2 microns is also the resolution for diffraction-limited optical microscopes. You can only see them clearly with an electron microscope. So that's a bit more of a challenge already. I'm going to suggest bypassing all this with an open-ended approach, starting with a telerobotic facility in orbit and only returning to Earth if you know exactly what's in it and what precautions to take. But first, let's continue and see what the problem is. So next came the announcement of fossil Martian nanobes in a meteorite far smaller than ultramicrobacteria. This soon became controversial and the debate about whether it is life or non-life continues. Anyway, that's the background to this 1999 workshop. How small can life be? Modern cells use ribosomes for catalyzing cell processes. These are huge molecules 20 nanometers in diameter upwards. They're made of RNA, shown in blue, folded together with proteins. If you had, say, a 50 nanometer cell, you can't fit in many 20 nanometer ribosomes, and to translate DNA to RNA, you also need the bulky DNA polymerase and many other things. So the ultramicrobacteria are probably as small as modern Earth life can get, apart from viruses, of course. But what if we have only one informational polymer, such as RNA, or could be PNA, TNA, etc.? That would simplify it hugely. To start with, you can drop all the bulky DNA to RNA translation machinery. Then, the RNA needs to catalyze its own replication and form enzymes for other cell processes. So you still need something to take the place of the ribosomes, and for a while they were stuck. Because RNA is not as bendy as a protein, so how can it make these complex shapes? But then they discovered that nature has found a way, the ribozymes. These aren't folded. They consist of lots of RNA fragments joined together, and not even sequential RNA, but from different places in the strand, and these are as tiny as a few nanometers in scale, so now you can pack a 50 nanometer cell with 1,000 ribozymes. With redundancy, that could be 100 different functions, so potentially we now have a robust, complex cell. We don't know how to do this, of course. You can also argue that the ribosomes and cell machinery of the modern cell is just far too complex to arise spontaneously in one go from non-living precursor cells, so must have been less complex early life. Then looking at smaller cells, they reckon the smallest you could still call alive could maybe be 5 genes, and that could be 80 nanometers in diameter, including the wall if spherical, and if elongated, only 10 nanometers in diameter, internal diameter just 2 nanometers, still wide enough for the ribozymes. Result, by coincidence or otherwise, is similar in size to the larger Martian nanobes. Then we also need to look at horizontal gene transfer. It's least possible that Enceladus and Europa ocean life is related to us by a meteorite from Earth, or both seeded by life around another star. Here, researchers have found bags of seawater collected from many coastal environments, just with whatever microbes are in them. They added a gene transfer agent engineered to give antibiotic resistance, which is easy to detect. By next day, 47% were antibiotic resistant. With no reason to need it, they just took up the capability from the GTAs. Here we are talking about microbes that are far more distantly related from each other than animals are from plants. So it must be an ancient mechanism, and so, if we have a common ancestor with Enceladus or Europa life, we could share capabilities with this life via GTAs. Those are tiny, of order tens of nanometers, consist of a fragment of a gene and a protein coating. So what is the result? First, we have the unusual requirement to both contain life and also simultaneously exclude even a single amino acid getting in. This needs a new type of facility, positive pressure in both directions, outwards and inwards, and probably double-walled. It should be designed to contain particles as small as 10 nanometers, they concluded. If this was not possible, a 50 nanometer particle, they said, must not escape under any circumstances. That's your 1000 ribosome cell. A decision to increase above 10 would need a new review by an independent group of experts. The results also need to be reviewed based on new research, so perhaps recent developments in synthetic minimal cells or XNA biology. Then they recommended the staff have to be trained and facility ready to run several years before the launch of the return mission. That's to deal with issues of human errors and the novelty of the facility, and need to respond rapidly to any unintended release. Here is an example design, everything handled by telerobots with no humans inside. These facilities might well cost $500 million upwards, and might take around 12 years from initial planning to reach the point where it is ready for a sample return launch. All of this just to return less than a kilogram of material. It's got a bit beyond the early ideas of a glove box now. Then Margaret Race of SETI did a study of the legal processes involved, and the timescale is rather similar, 10 years. Back at the time of Apollo 11, equivalent legislation went through in 1 day. They published quarantine regulations on the day of launch. There was supposed to be full public debate, but nobody got to check it or change it. Totally unacceptable nowadays. Carl Sagan was dismayed that the returning astronauts just got out of the capsule in their decontamination suits into an open dinghy. Remember, lunar dust got everywhere inside and on their clothes. Most likely some dust got into the ocean at this point. You would hardly find a worse place to contaminate with extraterrestrial life. Why, one wonders? Well, they had a last-minute problem with the crane to pick the capsule out of the water. Rather than leave astronauts to get seasick, mission planners took them out right away in a dinghy. It's not surprising, but shows how humans tend to react when there are tiny probabilities of high hazards. More immediate concerns take priority. I think we should treat Apollo precautions as almost entirely symbolic. It showed that we cared. But by the end of the 19th century, they already knew the moon didn't have an atmosphere. So it was a precaution against something most people thought wouldn't happen. And even with the science we have now, there's nothing they could have done then anyway, as they didn't even know about many of the potential hazards like the ones I touched on. We were just lucky that the moon had no hazardous life on it. So in short, the quarantine regulations of Apollo had no public review, were largely symbolic, were based on now outdated science, and they have been rescinded. We have to make a fresh start. So that's the first thing, to clarify the quarantine laws, which could include legislation for what you do in case a staff member is contaminated during mistakes made inside the facility. This could also involve consideration of human rights. Can you legally keep someone in a facility for such reasons? Then she looked at the US domestic laws. The process starts with a formal environmental impact statement and public hearings, which take several years. The Presidential Directive NSC 25 requires investigation of any alleged impacts on the environment, and it has to follow after all the other legislation is completed, and takes another several years, ending with presidential approval. Then you have numerous international laws on environment protection and health that didn't exist in the Apollo era, and then quite probably other countries' domestic laws could be relevant too, because the worst case impacts on the habitability of all countries. So for instance, if the ESA returns samples, say to France, then the US might well still have to pass all this domestic legislation, since potentially it could impact on them also. If there was no opposition at all, the process would still take around 10 years, she thought. Then there are other things not covered by the study. What if a sample return capsule is damaged as happened to the Genesis probe? This is not a back contamination hazard, since it just sampled the solar wind. But as a sample return from Enceladus to Europa, then we must be sure the container can't be breached under any circumstances. That includes also checks to make sure it wasn't breached by a micrometeorite in transit. Then there are other human factors that are harder to quantify, including overall mission design errors, crash of the recovery vehicle, various human errors, and accidental or deliberate release later on. You might wonder, what about the sample returns we've already done from comets and asteroids? though it's a minority view, some think that there might be a possibility of life there. This shows the Hayabusa sample return, which crashed, but the sample was from an asteroid not expected to include life or life processes. This is the assessment for Hayabusa 2, which is due to visit a large, slightly less than 1 km scale carbonaceous chondrite meteorite. This is unprocessed material from the early solar system, rich in organics, which could have liquid water in the past, so potentially habitable in the past. As you see, they use decision trees. And as you pass through, you see that there's some possibility of life from freshly excavated material. But they were able to pass it for planetary protection because we got something like 40 tons of asteroid materials every year on the Earth, like this Perseid. And some of them will be carbonaceous chondrites. The interior of a meteorite typically stays very cold. Cold is for interstellar space even, while the crust is melted. And smaller ones land gently with low terminal velocity, like a Mars falling off a skyscraper. So whatever there is in them, whether life or not, we are clearly evolved to be adapted to it, so this passed with no special requirements needed. However, when it comes to Europa and Enceladus, deep in the gravity wells of their parent gas giants, there's almost no chance of a meteorite making it all the way back to Earth. So there's no natural influx and we have to take stringent protection measures. Most of the discussion has been on the effect of microbes on Earth hosts. This is Joshua Lederberg's assessment that the microbes would not be adapted to infect us, but on the other hand, our immune system would not be adapted to recognize them. If it didn't produce the carbohydrates and peptides typical of Earth life, then it would essentially be invisible to our bodies. There's been a lot of focus on that, but I'd like to have touched on a couple of other things of special interest for the Titan moons. First, the idea that XNA-based life could be better than Earth life, so it could be an all-round better metabolism. Or it could be that, for instance, it's better at photosynthesis. So you might wonder, how could life in the Antarctic Ocean develop photosynthesis? Well, it turns out that a form of sulfur bacteria has developed the ability to photosynthesize with infrared light from a hydrothermal vent. We have three main forms of photosynthesis on Earth: the type used by plants, with variations, the type shown here, which doesn't produce any oxygen and uses hydrogen sulfide in place of water, and then the method used by the haloarchaea, which turns red to red. These convert light directly to electrical potential by a similar process to the way that we see light. So, what if life on Enceladus uses another method, called photosynthesis Mark IV? And what if that is more efficient than any of these? Thus, the idea of XNA-based life creating chemicals that confuse our biochemistry. In this case, a small molecule created by green algae happens to closely resemble an amino acid and gets misincorporated into proteins and may cause folding disorders like Alzheimer's, one of the reasons why you shouldn't eat seafood from an algae bloom. So there's no advantage to the algae to give human Alzheimer's. It is just an accidental side result. With an alien biochemistry, it might easily create various small chemicals that either confuse our biochemistry or get misincorporated by our bodies, so we might all get Alzheimer's, for instance. This was another possibility. This is a small, harmless, short-horned grasshopper, just hops about doing no one anyone harm. You can easily imagine if you brought back something as harmless seeming as this, it would seem totally innocuous. But every few years, due to some trigger or other, it turns into this. A plague of locusts. So why not just bypass all this and return our sample to orbit? You would think immediately about returning to the ISS or a purpose-built human facility. However, I would suggest that won't work. First, it's not all about humans. What if trees or grass or cows or sheep or whatever we are impacted, we can't take them all up to space to test them? Then Carl Sagan, you might know, but as well as a science presenter, he was one of the first astrobiologists. He raised the vexing question of the latency period, the time before the parasite does anything. For a known hazard like rabies, then if your dog doesn't have it after 4 months, in the case of the more recent UK regulations, it probably doesn't have it. In the case of leprosy, this period can be several decades. We saw that the Apollo quarantine regulations were not given public review. If they were, biologists might have said that they would have to stay there for decades if you want to be sure, rather than the 3 weeks largely symbolic period that was used. And in any case, there's a potential violation of human rights. Even if they agree to it, it's not clear you could legally hold them to it. And anyway, imagine if one of the astronauts became seriously sick. We saw how they reacted to just the prospect of seasickness. In this case, then they would have been removed from the facility immediately and taken to hospital. They'd say, we did our bit, but now they are in danger, so the astronauts have priority. So I don't see that working at all. There's also the idea of returning it to a quarantine facility in orbit with no humans on board, but then the life might be dormant in whatever conditions you find there and wake up later on Earth. Or they might start off requiring some restricted conditions, like for instance alkaline soda lake conditions, and then if they return to Earth, then they evolve the ability to live more widely. So, in short, human quarantine is just symbolic, unless you know what it is that you're quarantining. Quarantine tests of life forms from Earth tell us little. There's no substitute for knowing what it is before you let it anywhere near to humans or Earth itself. So that leads to my suggestion. First, study in orbit with telerobotics. So far, we have never studied anything like this in space. With Mars, it's not just a time lag. Some forms of telerobotics can be done with this 8 minutes time lag, but use simulated real-time, local real-time, and technique for online gaming. But the bandwidth is so small that typically we send commands for an entire day and rely on information returning to make the decisions for the next day. So our Mars rosas could be as far away as Pluto, and we would do it exactly the same way. However, technology is very advanced now. This shows the Da Vinci system of telerobotic surgery. He looks into the machine and manipulates instruments with his hands while the patient lies over there to his left. This permits more precise surgery with delicate tools. He would as easily operate from his office or somewhere else entirely, except that for safety reasons he is required to be in the same room. And they did actually test telerobotic surgery. A patient in France was operated on in this way by a surgeon in the States. They had a team of doctors on hand in France ready to step in, but they were not needed and the operation was a success. It's not widely known, but the Japanese are planning to build a large radio telescope in orbit, assembled by telerobotic methods, and they have already tested this in orbit and shown that it can be done successfully. So, on to my idea. So, our aim is to get a capsule to above GEO orbit. I'll explain why. But the idea is to use a similar approach to the NASA asteroid return mission. Returning the sample to the Sun-Earth L2 position first, which is where the Earth and Sun's gravity pulls are in balance, shown here, EL2. Once you've got that far, then there's almost zero delta V transfer, a method that can get you down to lunar L1, and we are well into the cislunar space. It's not so easy to get to the Sun-Earth lunar L2 because it's not so easy, in other words, to be captured by the Earth-Moon system, because we must always bias our trajectory away from Earth, so that a failure can never lead to an impact on the planet. And this rules out close flybys of Earth and the over-Earth effect, which magnifies the effect of your rocket propulsion if you're near to a planet. This was used, for instance, by the Indian Mon mission. And so this restricts what we can do quite a lot, and we mightn't be able to do it with a gravity assist. Perhaps we would need get rid of 2-3 kilometers of extra delta V, similarly to the Rosetta's escape velocity when it first left the vicinity of the Earth. Anyway, experts would need to sort out the technical details here. I'm just touching on some of the possible considerations. But that doesn't seem to be an impossible amount to find, because you have a very large, you can easily have a very small capsule and a large, in other words, a large fuel to capsule ratio, or you could use ion propulsion as well. Anyway, so you get your L2, you get your L1, And then once you get to L1, it's easy to get into this very interesting orbit called the distant retrograde orbit around the Moon. And in this situation, it's actually an orbit in the same direction as the Moon, but it's elliptical, and when it's closer than the Moon, then it's faster, so it kind of catches up. And when it's further away, it's slower. So from the point of view of the Moon, it's actually a retrograde orbit. And the good thing about this is that it's very stable. It's about 100 years stability. So once you've got there, there's no huge hurry for the next step. The next step is to send an unmanned spacecraft from Earth to capture the capsule. And then this will be the start of our telerobotic facility. The natural place to take it is to above GEO, say 5,000 kilometers above the geostationary satellites and their graveyard orbits, so well away from anything. That's 1 kilometer per second delta V to get back to the Moon, and it's over 1 kilometers per second delta V to get to a geostationary transfer orbit to hit the Earth. So it's now as safe as it can possibly be in cislunar space. This is probably a decade or two from now. We probably already have the capacity to send 100 tons or more in one go to above GEO by the time we get to this stage, this future. So it's easy to send large machines up there to study it. And we're doing this, of course, to benefit all humanity as required in the Outer Space Treaty. So individual countries, such as, say, India, could mount their own expedition. The only requirement is that all materials have to be transferred only one way to the facility, and of course no humans that go anywhere near. It might be that you find that there's nothing there except amino acids and maybe autopoietic cells, but no life, and everything is so feeble it would be eaten easily by Earth life. If so, totally sure as a consensus, you could return to Earth. And so you're completely safe, there's absolutely no need for this facility or all those new laws, because there's no life in your sample anyway. And then, on the other hand, you might find an exotic XNA-based life, and say you find it's got a more efficient metabolism than Earth life. Then at that point, everyone would agree that you have to take extreme care, and in that case you might not return for a considerable period of time, except possibly sterilized samples. And if you did, everyone would understand the need for an elaborate facility to contain it, and would take great care, and would have all their attention focused on really stopping it. So this is an open-ended approach, where at each stage you know the implications of what you're doing, and you don't have to rely on making probability assessments that really exobiologists haven't got anything like sufficient data to provide. So that's my suggestion.